So in this video, we're going to look at a topic called dielectrics. So we had an example where we wanted to figure out the dimensions of the capacitor we would need to create if we wanted, I think it was like a 5 microfarad capacitor, and it took two plates that had an area of like 5 or 6 meters squared. So a pretty ridiculous capacitor to make that amount of capacitance. So we're going to look at this topic will show us how we can make a capacitor like a 5 microfarad capacitor, which is a pretty normal capacitor. How can we make one with a reasonable size? And so let's just say that we have a battery here. So we're gonna connect a battery to a capacitor, and we're going to let it charge up. Right, so here's our battery, and we're connecting it to this capacitor. It's going to charge this thing up, and let's say that it's going to have charge, let's say it has charge Q naught. So it's going to charge the top plate with a positive Q naught, the bottom plate with a negative Q naught. And it's going to have the same potential difference as the battery. So this is potential of the battery. Okay, and so the potential, and I'm going to call it, just to kind of stick with this notation here, I'm going to call it delta V naught, but just know if I'm connecting this to the battery, it's going to have the same potential. So delta V naught, which means that it's going to have a capacitance of C naught. And remember, capacitance is the charge to potential ratio. So capacitance of this capacitor, C naught, is equal to Q naught over delta V naught. Okay. And so then I'm going to disconnect it from the battery. Okay, so kind of looking at this when this is disconnected. So here's our top plate. Here's our bottom plate. The other thing I want to make sure we define here is the electric field. So we do have some positive charges up here. We have a positive plate, and we have a negative plate down here. And this thing is going to have an electric field where the direction of the field would be going from the positive plate down to the negative plate. And we are going to call this electric field E naught. So this is the electric field E naught. Okay, and so what we're going to do here is we are going to insert an insulator. All right, and let's talk about what would happen if we did that. So at this point, again, this is disconnected from the battery. So the one thing that is not going to change since it's disconnected from the battery is the amount of charge on the plates, because they have nowhere to go. So when we do this, we're going to have, okay, so here's a capacitor again. Now we're inserting some material. We're inserting some material in between this thing. Okay, and so I'm just going to draw, use a different color just so you know it's some other material here. All right, so we're inserting a material in between this thing. Okay, and again, the amount of charge on these plates still has to be equal to Q naught, because we're disconnected from the battery. It has nowhere to go. So has charge Q naught. But what is going to change about this? Okay, so again, we have these positive charges up here, and we have the negative charges below. And so what's going to happen, again, this is an insulator, is the atoms in here, they are going to be polarized, right? So we're going to get, for each atom, we're going to get the negatives want to go towards the positive plate, where the positives want to go towards the negative plate. And so each atom in here is going to be polarized. So it kind of looks like this. Each atom is polarized. And what we can do, so notice that we have a net positive on this side, right? This side of the material, it has a net positive because most of the positives are down there. And then this side of the material has a net negative. Okay, and so what we would get is some kind of electric field on the inside of this dielectric. So we have some kind of electric field if we pretend that basically this is a negative plate up here and this is a positive plate down here. We've got an electric field inside this dielectric, inside this insulator, that is pointing from the positive up to the negative. So so we have this electric field in here. We're calling this E induced, which is going to change the net electric field inside our plates. So remember, we still have this electric field out here, E naught, going from positive to negative, which is going to be stronger than E induced. And so then the net electric field, so the new electric field, is still going to be pointing down, but it's going to be changed, right? So the new electric field E, what is that? What is the new electric field? The new electric field in between our plates is going to be equal to E naught, the electric field before we put the dielectric in there, minus E induced. E induced is, again, that electric field inside of the insulator. That insulator that we slid into the capacitor, that is what a dielectric is. That's what we call a dielectric, okay? So what happened then? So by putting this insulator inside of our capacitor, the electric field changed. It actually decreased, right? So we decreased the electric field by doing that. E is less than E naught, clearly, because we're taking E naught and we're subtracting something. If that happened, and so if that happened, remember delta V, or the electric potential, so electric potential is proportional to electric field, right? The more electric field you have, the more potential you have. So that means that the electric potential, delta V, must have also decreased. So delta V of our capacitor changed. It's less than delta V naught. Okay? And this implies that, well, since the capacitance is equal to charge over delta V, and since charge did not change, right? This Q here did not change. It still equals Q naught because it had nowhere to go. Delta V decreased. If the denominator decreased, then that means that the entire number must have increased, which means the new capacitance is larger than the old one. So the new capacitance is greater than the old capacitance C naught. Okay, so we've been able to increase our capacitance just by inserting an insulator in between our current capacitor. All right, and so we're going to define something new here. This is going to be the dielectric constant. So we're going to define dielectric constant. All right, we're going to give this the symbol kappa. It's a Greek letter, looks like a K. And we're defining this as the electric field, E naught, so the electric field of a capacitor with a vacuum, so there's nothing in there, divided by the electric field, the new electric field, after we've inserted some kind of material in there. Okay, so this Greek letter kappa, whatever value, so depending on the material that is put into our capacitor, either the problem will give us that value or they will ask us to find it. So this is the Greek letter kappa, and again, they'll either ask us to find it or they will give the number to us so that we can use it. Okay, and so if we're going to define kappa as the electric field, the original electric field divided by the new electric field, then in this particular case, that means that the new potential of the capacitor, delta V, the new potential, we can also relate that to kappa. So the new electric potential is equal to the new electric field times the distance, so the distance between each plate. So that doesn't change. We didn't separate the plates, so this would be D. Okay, and we just defined, we just related the new electric field to the old electric field E naught using this new this new constant kappa. So electric field here is going to be equal to E naught over kappa, E naught over kappa times distance, and E naught times distance, this would be equal to the old potential, or the potential of the battery. So this would be equal to a delta V naught over kappa. All right, and then we can also relate kappa to the new capacitance. So again, capacitance is equal to the amount of charge divided by delta V. Again, charge did not change in this case, so charge is equal to Q naught divided by delta V. And we just said that delta V is equal to delta V naught over kappa, so this would be equal to kappa times Q naught over delta V naught, and this value here is equal to C naught, right? The old capacitance. So the new capacitance is going to be equal to kappa times C naught. And by the way, kappa is always greater than 1. It's a value greater than 1. Okay. So in the case that we just looked at, we disconnected the battery after we charged the capacitor, and then we inserted the dielectric. But what if we keep the battery connected? Okay, so in this case, we've got our battery. And this time, after we charge this thing up, then we're going to insert the dielectric, right? So insert dielectric. So now what's going to happen? Well, before the electric potential decreased, but since it's connected to the battery, then even after we insert the dielectric, delta V cannot change. The electric potential of our capacitor is going to equal the capacitance, or is going to equal the electric potential of the battery. So delta V after we insert the dielectric is equal to the electric potential before we inserted the dielectric, which is equal to the electric potential of the battery. Okay. The capacitance is still going to change by the same factor. The new capacitance is still going to equal kappa times C naught. Remember, this is just kind of a property of before it was just the property of sort of the dimensions of our capacitor, but now we know it's a property of not only that, but also the material that we put inside the capacitor. So that's just kind of a property of the material. So what is going to change if delta V doesn't change and capacitance doesn't change? Then what is going to change? So again, capacitance is equal to Q over delta V. All right, and so if delta V is going to remain the same, if this time this remains the same, then that means that the charge is going to change. So this is going to do something. Well, since capacitance is equal to charge over delta V, and again, the capacitance is equal to kappa times C naught, and C naught is equal to Q naught over delta V naught. Since delta V's are the same, right? Delta V is the same as delta V here, then that means that charge Q, the new charge, is equal to kappa times Q naught. So the amount of charge on our capacitor must increase in that case. So just to summarize a couple of things here. Okay, so just a short summary. So when we insert a dielectric between the capacitor two things always happen. Okay, always. So the electric field, so this always happens. The electric field, the new electric field after we insert the dielectric is going to be equal to the old electric field, E naught, divided by kappa, that dielectric constant. The capacitance of our capacitor is always going to increase by a factor of kappa. So kappa times C naught. That always happens no matter what we do with the battery. If we disconnect the battery, so if we disconnect the battery after we have charged the capacitor, but before we insert the dielectric, so we disconnect the battery before inserting the dielectric, then we are going to, we're not going to change the charge. So Q will equal to Q naught. Charge doesn't change, but delta V does. The electric potential will change. Electric potential, the new electric potential is going to be equal to the old electric potential divided by kappa. And then if we leave the battery connected, then that means that the electric potential is going to remain the same. So the new electric potential just equals the old electric potential, but the charge will increase. So the charge on the capacitor Q will equal kappa times Q naught. And then just a couple of other useful relationships that you can get from these other relationships that we've found. So a few other things. Again, electric field, the new electric field is equal to the old electric field, E naught, minus the induced electric field, which is equal to the old electric field divided by the dielectric constant. Okay, which implies, if you do some algebra here, this implies that the induced electric field is equal to the old electric field times kappa minus 1 divided by kappa. Okay, and then another useful relationship is the induced surface charge density. So when I say the induced surface charge density, that would be the, so again, looking at this dielectric, use a different color here. Again, it's as if the top part has some kind of negative charge and the bottom has a positive charge. And we could figure out, well, what is the induced surface charge density on there using the relationships we have already found. And I encourage you to prove this to yourself, but that induced surface charge density is equal to surface charge density on the plates times 1 minus 1 over kappa. Okay, and I encourage you to see if you can use these other relationships to figure this one out on your own. And so look in another video for an example kind of applying this new concept.